All right, so we're going to take a look at 7.2 Part 2. Luckily, most of what we did in 7.1 Part 1, you don't need to remember. Anything that you do need to remember, I just showed you guys. SOHCAHTOA, inverse trig, Pythagorean theorem, and was that other thing we showed? Oh yeah, the rationalizing denominators with square roots. So, the goal in the first part of this section, and I think the first part is harder than the second part. The second part's easy. First part's a little harder. Is you're going to have a formula like that. That's a trigonometric formula, okay? Because it has trig in it. We're not doing it yet because I got some things I need to explain how to do first. Okay, but when we get to it, that's what a formula is going to look like. The goal is going to be to take a formula that looks like that, or like that, and get rid of all the trig. Okay? So there's not going to be any trigs. You're going to come up with a formula that gives you the exact same result, but it's not going to have sines, cosines, and tangents in it. It can have addition, it can have subtraction, it can have division, it can have squaring, it can have square roots, it can have powers, it can have anything you want in the formula except trigonometry. Okay? So it's going to be converting a trig formula to an algebraic formula. Okay? And I'm going to show you guys kind of how to do that. So the trick is to start with the inner trig function. When I say inner, I mean this one. Okay, forget about the outer one for now. You're going to need it, but it's going to be the very last thing you do. So you're going to start with the inner trig function. And what we're going to do is we're going to take the inner trig function and we're going to draw a diagram of it. So we're going to end up taking this part of the problem and turning it into a picture. That's the first step. Now, in order to do that, we are going to have to rewrite it a little bit. Maybe after a while you won't need to do this step, but at first it's going to make more sense if we do it. If that inner trig function is inverse trig, which it is in this one, I'm going to want to rewrite it using regular trig. So what we're going to have to do is we're going to have to cancel out the inverse cosine using a function that's the inverse, and we just talked about that. So I'll show you how we do that step. Pythagorean theorem is going to come up here, and that's all you really need to worry about. Okay, so usually at some point in these problems, you're going to have a triangle, you're going to know two sides, you're going to have to find the third side, and you're going to use Pythagorean theorem to do it. The key is you're not going to have any numbers. It's going to be all letters. Well, I take that back. You might have some numbers in it, but it's not going to be all numbers. There's going to be letters mixed in. Okay, so that's the general idea. Now let me show you how we do it. Okay. So first thing we want to focus on is the inside function, okay, which I've circled. So this problem is the sine of the inverse cosine of v. Could be v, could be x, could be the letter here, doesn't matter. So what I'm going to do is just copy over the inside trig function. Now, we learned back when we did the SOHCAHTOA that inverse trigonometry, doesn't matter if it's inverse sine, inverse cosine, inverse tangent. Anytime you do inverse trigonometry, you are solving for an angle. That's what inverse trigonometry does. Okay. So if on my calculator, I type in something like 0.8, and I do the inverse sine of 0.8, that answer that I just got right there, that's an angle. Specifically, that's an angle in radians. Okay. Anytime you do inverse trig, answer is an angle. So what I'm going to do is I'm going to say, you know what, I don't know what the inverse cosine of v is, because I don't know what v is. but I know when I do the inverse cosine, the answer is going to be an angle. So this just represents a generic angle, some angle. And now we're going to take this equation and we're going to rewrite it. The way we're going to rewrite it is to use regular trig. So what I want to do is I want to cancel out this inverse cosine from on the left. So what would I have to take on both sides to cancel out the inverse cosine? Yep, there. Cosine. So what we're going to do, I'm just going to kind of, over here I got plenty of room. I'm going to take the cosine of the left-hand side, and I'm going to take the cosine of the right-hand side. Just like if you had an equation like this, and you said, I'm going to take the square root of both sides. You do it here, you do it here. It's exactly the same thing I did up above. Took the cosine here, took the cosine here. Did it to both sides. Now, if I put that back for a second, square and square root cancel. Cosine and inverse cosine cancel. So now you're left with another equation that says V equals cosine theta. Now I want to draw a picture of that. That's what I want to draw a picture of. So I'm going to set up a right triangle diagram. It does not matter where you put theta. It doesn't matter at all. You're going to get the same answer no matter where you put it. I'm going to put it there. Now, I'm just going to move this so I have a little more space. What did we say when I was reviewing with you guys? Cosine is equal to what over what? Jared?
Adjacent over hypotenuse.
This is equal to adjacent over hypotenuse. Right? So I need to label two sides in this picture. The two sides that I'm labeling are the adjacent and the hypotenuse. Now, you have to label this and you have to label this so that when you divide them, the answer is V, because that's what the equation says. It says when you take the cosine, you should get V. So we have to label this side and that side. You can put whatever you want for the bottom question mark. You can put whatever you want for the hypotenuse. The only condition is when you divide the adjacent by the hypotenuse, it has to equal V. So the way I would do it is I would think of V exactly like you have right there. Think of it as a fraction. How could you make V into a fraction? Yeah. 100. So now, the top of your fraction is the adjacent, and the bottom of your fraction is the hypotenuse. So now if you take the cosine of this angle, you would have V divided by 1, adjacent over hypotenuse. And that's exactly what the equation said it should be, because this is what you had originally. The cosine was supposed to come out to V, and in that picture it does. Now, the last part is they want the sine of what I just circled. What I just circled is represented in that picture right there. So what they basically want now is the sine of that picture. Now, you're going to think for a second, what's sine? What over what? Yeah?
Opposite over adjacent.
Opposite over adjacent, I think it was on another page. Opposite over adjacent was tangent. We might use that one a little bit. Okay, so I got to take the sine of this picture and it's opposite over hypotenuse. I've got hypotenuse. I don't have the opposite. Okay. I have 2 out of 3 of the sides in this triangle. How do you get the third side when you know 2 of them? What do you use?
Pythagorean theorem.
Use the Pythagorean theorem. So if you want, you can call this x for now. I'm going to erase that x in a second because I'm going to have a formula for it using the other two sides. So 1 leg squared plus the other leg squared equals the hypotenuse squared. And now solve for x. Right? So we can go x squared plus v squared equals 1, because 1 squared is just 1. How would we move the v squared to the other side? Yep. Yep. Subtract. Subtract. There's not really a lot you can do other than just write x squared is 1 minus v squared. And now I want x. So what do I have to take on both sides to get rid of that exponent of 2? Take the square root of both sides. Square root and square cancel. And that is the length of this, is basically the height of that triangle. It's the square root of 1 minus v squared. Okay. That's the hard stuff. Okay. Now we just have to write the final answer, but all we have to do is look at this picture. Okay. I gotta go back up because I don't remember what they said. They want the sign. Sine is opposite over hypotenuse. Opposite divided by hypotenuse. Square root of 1 minus v squared divided by the hypotenuse is 1. Do I have to put divide by 1? Does that make a difference? No. So what I just circled right there is exactly the same formula as what's on the left. On the left is trigonometry. On the right, no trigonometry. Okay? And we'll do 1 or 2 more so you can kind of see, but it's the same pattern every time. But now I'm going to show you they're the same. Let's take what's on the left and type in sine of inverse cosine of x. And on this one, type in the square root of 1 minus x squared. And I'm going to do zoom 7. What you're looking at is a graph of what's on the left. Now you're looking at a graph of what's on the right. It might have been hard to see. Let me zoom in so you can see it again. That's a graph of the left-hand side. That's a graph of the right-hand side. They're exactly the same. Yeah. Okay. Yeah, you can go ahead.
11 point.
Okay. So you might have noticed when it graphed it, the one in blue was kind of like blocky, like it kind of was. It took a long time to do it, but the one in red was a little bit faster. So that might be a reason if you were making a computer program. Why would you care to even do this? Well, maybe this formula on the right is more efficient. Maybe a computer can do square roots faster than it can do sines and inverse cosines. So sometimes when you get into making things on a computer, it's not only can you do it, but can you do it better? Can you do it faster? Yeah, we already can do it, but let's make it even better than it is. And that's the general idea for all of these types of problems. So let's try another one again. And now I'm going to ask you some more questions rather than me just kind of doing the whole thing. Okay, which trig function do I want to start with? Yeah.
Inverse sine.
Yep, inverse sine. Start with that. Inverse sine of v equals, and what do we always set it equal to?
Theta.
Yeah, set it equal to theta. Whenever you do inverse trig, the answer is an angle. What angle? I don't know. It's going to be an angle. In fact, the angle doesn't even matter. Now, eventually we want to draw a diagram, but first I need to rewrite this. I don't want to have inverse trig. So what am I going to do on both sides now to get rid of the inverse trig? Yeah. take the sine of both sides. Just like taking the square root of both sides. Take the sine. Sine, inverse sine cancels. Brianna, what's my new equation now? V equals sine of theta. Okay. Now, we have that. We're going to represent this a little bit differently now. Rather than as an equation, what am I going to do now? And this is going to help me to do it. Yep.
Diagram.
What kind of diagram?
Right triangle.
Yep. I'm going to set up a right triangle diagram. Does it matter where you put theta? No. What does matter is that you label the correct sides. Can someone remind me what's sine? It's what over what? Yeah, Tim.
Opposite over hypotenuse.
Okay. So he just told me the two sides I'm working with. Opposite, hypotenuse. I need to label those two sides so that when I divide the opposite by the hypotenuse, I get V. So based on what we did last time, anyone think they could tell me what I should make the opposite? Yeah. V. And what about the hypotenuse?
1.
1. Yes. Now, I had somebody in another class say, well, could you do 2V and 2? You could, because 2V divided by 2 is still V. That's more complicated. The one Jerry gave me was simple. Okay, so now we got our two sides. Scroll back up. They want to know tangent. Kaya, what's tangent? Opposite over adjacent. Opposite, we're good, we got it. Adjacent, no, we don't have it. So, Chris, how do I find the adjacent using the two sides that I know? Yep, use the Pythagorean theorem. So, Eric, can you set up the Pythagorean theorem temporarily? We'll just call that x.
X squared plus v squared equals 1 squared.
Yeah, and if you notice from the last problem, x squared plus v squared equals 1 squared. Where is it? X squared plus v squared equals 1 squared. It's the same equation again. So you're going to see that set up a lot in these problems. Okay, so we already know what this comes out to. Square root of 1 minus v squared. Okay, so let's put that in right here. Now that you've labeled all the sides, you're good. You can answer any question they want to know. They want to know tangent. Tangent, Kaya just told us, is opposite over adjacent. So let's write the answer. Opposite is V divided by adjacent, square root of 1 minus v squared. Now, as far as getting rid of the trig, we're done. But we can't leave that as our final answer. What happened there? It didn't happen in the last problem, but I told you when we did the warm-up that it could happen, and it did here. Yeah? There's a square root in the bottom. We can't leave that square root in the bottom. And I think it was Jared during the warm-up told us how to fix it. We multiply top and bottom by whatever's in the bottom. And then that gives you v times the square root of 1 minus v squared. Not much you can really do with that. And in the bottom, the square roots cancel, and you just have 1 minus v squared. Okay, I'm not going to graph that one, but if you did, that'd be a good way to check your answer. And then see if the graphs look exactly the same. If they do, you did it right. Questions on that one? So it's a little weird, but once you get used to the process of doing it, it is the same process as long as you have regular trig on the outside, inverse on the inside. Okay. Let's try this one. So The difference here is this says evaluate. Evaluate means when you're done, the answer is a number, like 5. Okay, what time is it at? 11:20?
It was supposed to be 11.
Oh, it's supposed to be 11?
Yeah.
Yeah, that was different.
Oh, okay, yeah. Just sign off. So, if they're asking you to evaluate this without a calculator, then that means it must be special. It must come out to a nice answer somehow. So, based on what we did last time, what trig function do you think I'm going to start with? Yeah. So we got to pick one of the ones that's up there to start with.
Oh, start with the inside.
We're going to start with the inside one. We're going to start with tangent. Big difference between this problem and the last one. Regular was on the outside, inverse was on the inside. This time inverse is on the outside. This is not the same kind of problem. It's different. So let's start with the tangent of 3 pi over 4. My first goal is to figure out what the tangent of 3 pi over 4 is. Now, it might help if I think of it in degrees. How much is pi over 4 in radians? So this is triple 45, which is how much? $135. So we're trying to find the tangent of 135 degrees. 135 is a multiple of 45. Anytime that you're working with a multiple of 45 or 30, you can do it without a calculator. So this one is going to be doable. If it was like 140, no. You need a calculator to do that. So, the way we're going to do it is when we learned about unit circle trig, we're going to draw a triangle on here to help us figure it out. This is 0. This is 90. This is 180. Where's, Caleb, what's 135? Yeah, it's exactly halfway between 180 and 90. That's 135. So what I'm going to do is I'm going to make a triangle right there. Off to the side, I'm going to draw that triangle bigger so I can try to figure out what's going on. I'm kind of ignoring this sign right now. I'm not even doing anything with it. I'm treating this as 2 separate problems. I'm doing what's inside the parentheses as a trig problem. And then I'll come back and once I get that to finish it off. Now, first thing we have to recognize is what kind of triangle is this? I mean, it's a right triangle, but I'm thinking about angles. I mean, I know one of them's a 90, but how about the other two?
90, 30, 60, or the 30 and 60 are the other ones.
Well, figure out what this angle is. How far is it from 90 to 135? 45. So this part right here is a 45, which means this part right here is how much?
45.
It's got to be a 45 because that makes a 90. So this is a 45, 45, 90. I didn't draw it very nice. It's a 45, 45, 90 right triangle. Since 2 angles are the same, what kind of triangle is this? Yeah. That would be if 3 angles were the same, like 60, 60, 60. This one only has 2 that are the same. Yep. Scalene is all 3 different. Isosceles. Okay, it's isosceles. So, isosceles means 2 of the sides are the same. You can set this up however you want with your side lengths, as long as you draw it with 2 sides that are the same. Okay? We learned about trig, and it doesn't matter if you work with a triangle this big or you work with a triangle this big, or you work with a triangle this big. Similar triangles have the same trig functions for answers. Doesn't matter the scale. Okay? The sine of 45 is always the sine of 45. The tangent of 45 is always the tangent of 45. Doesn't matter the scale. So, two easy numbers we could pick. I would say, let's make this a 1, and let's make that square root of 2. How did I get that? I just picked two numbers that were the same for the isosceles sides, and I used the Pythagorean theorem to get the third side. If you wanted to do 3, and square root of 18, that would work too. But then you'd have to reduce later. So it's easier if you pick small numbers to start. Now, because this was 135, we have to remember something about our tangent. Something about this x value. Starting from the origin, which way does our x value go? To the left, which means it's what kind of number? Negative. So I know it doesn't really make sense to think of a side as being -1 units long, but because you're in quadrant 2, because that's where 135 is, you have to think of the x value as being negative. Okay? Can't forget that. And now, you do everything based on this angle right here. That's called your reference angle. I think we mentioned that before. But anytime you draw a triangle, it doesn't matter what quadrant you draw it in, you always use the angle that's right there. It's always the angle that's tucked in right near the origin. That's the angle you always want to use to do your problem. So in our case, right there. And you might be thinking, well, wait a minute, we're doing 135, we're not doing 45. I know, but we already made this side negative. That takes into account that it's 135, okay? Because you made that number negative. So you've taken care of the 135 part. So now, use this angle and find the tangent. Okay. Tangent of 135, opposite over adjacent. And what's 1 divided by -1? -1. So now, we know this entire part right there. You can change everything I just circled in red to -1. So now the last step is to find the inverse sign of -1. Now, if this wasn't a -1, I would say it would be tough to do. Actually, it would be okay to do if it was a 1, a 0, or a -1. If it's anything other than those three numbers, you're not doing it without a calculator. The reason you can do it as a -1 is because think of the graph of sine. It looks like this. Inverse sine of -1. What that really means is where on this graph do you hit -1? Well, what's the highest that this graph goes? And what's the lowest? So -1 just happens to be the lowest point that the graph ever hits. And -1 is 3/4 of the way through the cycle. Does anybody remember what 3/4 of the way through the cycle, what the x value is? Goes back to when we graphed the graphed sine and cosine. Yep. Yep, very good. That's 0, pi over 2, pi, 3 pi over 2, which is the magic number we're looking for, and 2 pi. If they asked me where this graph hit 1, I would have said pi over 2. If they asked me where it hit 0, I could have given two answers. Here and here. Okay. But they wanted to know where we hit 3 pi over 2, or where we hit -1. and that's 3/4 of the way through the cycle at 3 pi over 2. Okay, so that's the other kind of problem you could have. Okay? And the way you always do it is you start with the inside, draw a diagram, and this angle would always have to be a multiple of 30 or 45 if I'm going to ask you to do it without a calculator. It has to be. So what this part requires is that you know these two triangles. They're two triangles we've done before, but if you forget them, you'll get stuck at that step. Here's your 45, 45, 90. Or use anything similar to that triangle that you want to, but those are the smallest numbers that work out nice. 30, 60, 90. 1, 2, square root of 3. How do I know that? It's just something I have memorized. 1, 2, square root of 3. Could you prove those numbers? Absolutely. You use Pythagorean theorem and a little trick. But yes, you could figure out where these numbers come from. And I think we did when we went through it the first time. Okay. But if you know those two triangles, that'll help you with the second part. Okay, let's try one more of these, and then I'd probably going to skip that one, and then we'll do the last part, which is very easy on the graphing calculator. Okay. So this one, kind of like the last one, in that you don't have a letter, but look at the order of the trig functions. Where is the inverse? Yeah? Inside. You're going to do this problem exactly like you did example 1a. Exactly like you did example 1b. The only difference is now you're not going to have letters. You're going to have actual numbers that you can use to label the sides. But it's going to be exactly the same idea. Yeah. Yep. Okay. So Brandon, what trig function do we always start with? Well, in general, always start with the one that's where? On the inside. So in this case, it's, what's the one on the inside? Right. That does not say inverse tangent. So start with the inverse tangent. Then we're going to get to what he said in the next step. Anytime that you do inverse trig, what kind of answer do you always get? An angle. Doesn't matter what the angle is, you're going to get some kind of angle. We're just going to use that to draw a picture. We don't really care about what the angle is. So, in order to turn this into a picture, what do I have to do first to both sides of that equation? Chris?
Subtract tangent, inverse tangent both sides. You can't subtract inverse tangent. Just like if you had something like this, you couldn't say like subtract 2 from both sides to get x by itself. You've got to get rid of the square function with the square root function. So we have to use another function here. How do we get rid of inverse tangent? Taking. Yeah, there's no multiplying here. Just like when you do this, you wouldn't say you just multiplied both sides by the square root. You just took the square root of what was on both sides. Okay? Same thing here. We're going to take the tangent of what's on the left. That does not mean multiplication at all. And we're going to take
inverse tangent of what's on the right. So I should technically put that right there. So, tangent of inverse tangent cancels. And Jacob, what's on the left now?
The tangent or the left, sorry. The 1/2.
1/2, and on the right, tangent of my angle. Now I'm going to draw a picture, but you're not going to have to use any letters. It's going to be all numbers. Okay, Kaya, does it matter where I put theta? No. What does matter is that I label the correct sides. Chris, I'm dealing with tangent. What two sides am I going to label?
Adjacent and opposite.
And which one goes on the top, which one on the bottom?
Top will be 1 and bottom 2.
Yes, so the top is 1, the bottom is 2. Is the top opposite or adjacent though?
Adjacent.
Opposite.
Oh.
Yeah, so top is opposite, bottom is adjacent. Opposite, adjacent. Now, go back and look at the original question. They want the cosine. Sam, what's cosine?
Opposite over hypotenuse.
That's sine.
Or no, adjacent over hypotenuse.
Adjacent over hypotenuse. Adjacent, good. Hypotenuse, no, don't know it. So I have to figure out the hypotenuse. Caleb, how do I figure out the hypotenuse with those two sides? Yep. And if you do that, 1 squared is going to give you 1. 2 squared is going to give you 4. Add up 1 plus 4 and take the square root. Square root of 5. Now, we can answer this question. The cosine of the inverse tangent of 1/2. Okay. This is the diagram for inverse tangent. Now take the cosine of that diagram. So Brianna, someone just told us, what was cosine again? Adjacent over hypotenuse. 2 over the square root of 5. But, Nikira, what do I have to do to fix that? Where? Both the top and the bottom. So I'll just write it times that, and your final answer is 2 square roots of 5 over 5. Now, because this was all numbers, this is super easy to check. Type it in on your calculator. You don't even have to graph it. You could just do this without a graphing calculator. Cosine of the inverse tangent, I'm just going to do 0.5 because that's easier. And I get 0.8944. When I type in 2 root 5 over 5, it better come out to 0.8944. Let's see. 2 square roots of 5 divided by 5. 0.8944. But there's no way that the calculator would ever give me 2 root 5 over 5. It can't. The calculator is always going to give you a decimal, but you can get the exact answer if you do what I just showed. Okay? And that's all the work. Out of the two we looked at today, the one where the inverse is on the inside is more important in terms of like what you really want to focus on. The one where the outside had the inverse, I mean, might be like a good bonus question. But you're going to have at least maybe 3 of those on the test like that. Maybe some with numbers, and then some with letters. Okay, questions on? No. All right. Now, this one, we're not going to do it together. I just want to show you how quick you can do it once you get good at this, and you kind of get an idea of what's happening really quick in your head. I want to set up a right triangle diagram.
It helps if you draw a triangle. I want theta. I know the opposite is 1. I know the hypotenuse is 2. I can use Pythagorean theorem to solve for the third side. And now, take the cosine of that diagram, square root 3 over 2. I'm done the whole problem. That's the answer. So I went through it very slowly explaining everything, but when you get faster at it, you can do it about that fast. Let's check and see if I did it right. I could have made a mistake. Cosine of the inverse sine of a half, 0.866. Let's check what I got. Square root 3 divided by 2. Perfect. So when you get quicker at it, it doesn't take that long to do it. Okay. So last thing we're going to look at is something we've done before. It's basically like graphing in y1, graphing in y2, and then finding an intercept. So remember, trig equations are periodic, which means the pattern repeats itself. Let's say you graph that in y1, and you graph that in y2. Pretend that that's one cycle of the graph that you're looking at. How many answers are there based on the red and green lines that I drew in one cycle? Yep, 2. How about in the next cycle?
1.
So there's 2 answers in that cycle. If I were to draw the next cycle of that picture, how would it look compared to that cycle? Yeah?
The same.
It would look exactly the same as that. Copy and paste that, and you get the next cycle. So if there's 2 answers in that cycle, then the next cycle has 2. And the next one? 2. And the one before that one? 2. Every cycle has 2 answers. So remember, if you find at least 1 answer in a cycle, then there's going to be infinite answers. Right? Infinite amount of answers. And the way you represent all the answers, we talked about it earlier, is you have to put plus the period times n. Okay? So find all answers in one cycle. And for each answer, list it out separately, and then put plus the period times n, because that answer is going to repeat again exactly one cycle later. That answer is going to be that answer, same answer. And it repeats every period. Okay? So just put plus the period times n. Now, does anybody remember for basic sine and cosine, what's the period of sine? Yep. So the period of tangent is pi, which is 2 pi over 2. But the regular period of sine and cosine is just 2 pi. Okay, just 2 pi. If you have a question about secant, cosecant, or cotangent, is there a secant, cosecant, or cotangent button, Sam, on the calculator? No. So, if you had to type in secant, you're going to have to type it in by taking the cosine and flipping it. If you want to type in cosecant, you're going to have to flip the sign. If you want to type in cotangent, you're going to have to flip the tangent. Okay. Okay, so let's try this one. Sine of x equals 0.6. So, what Zach might have been thinking of when he said the 2 pi over 2 thing, I call that letter B. The formula to calculate the period is 2 pi over B. So he might have been thinking of that, but if you don't have anything in front of the x, it's just a 1. So the formula is 2 pi over the number in front of x. Number in front of x here is a 1. You'll never see the 1 written like that. On a test, I'll always do it like that. Okay? So the period here is 2 pi. Keep that in mind. Okay, who can tell me how I would type this in on the calculator and then what I would do from there? Zach?
Second sine from 0.6.
So if you press second, that would be that one. Is that the one that we have?
Oh, just normal sine?
Yeah, we just have normal sine. If you were going to solve it algebraically, I know what you're thinking. He basically did this. Second, inverse sine, 0.6. And yes, that is going to be one of the answers we get. I'm going to show you guys how to do more of that probably tomorrow. For today, all you have to do is this. Put sine in y1. Put 0.6 in y2. And then Brianna, we're going to look for where these two graphs lie. We're going to look for where they intersect. What I want to do so I don't get confused though, is I don't want to look at more than one cycle. Just set it to one cycle. So Caleb, we're in radians. What was the cycle for sine? That's a quarter of a cycle. 2 pi. So we're going to go 0 to 2 pi. Also, I need to set the highest and lowest. Jared had said earlier, it doesn't go higher than 1, it doesn't go lower than -1. So that's okay. You'll be right on the edge of the screen, but that'll work. So there's your graph of sine. We're going to get 0.6. And keep in mind that number that I showed you earlier when I typed in what Zach said. Just go back to it for a second. 0.6435. Keep that in mind. Okay. I'm going to go second, calc, intersect. And I'll move my cursor so it's closer to the intersection that I want. And notice it's exactly what he said, 0.6435. So there is a way to do it without graphing it, and it is faster. But it requires me to explain a little bit because now you need the other answer. Well, to get the other answer algebraically, you would have to do pi minus 0.6435. I'm going to explain more about how I know that later, not today. This is why I didn't do it algebraically, because you don't know that yet. But the other answer is going to be 2.498. Let's graph it and check it. So for you guys, you'd just be doing intersect. I think I said 2.498. Just remember that number. 2.498. So there is a way to get the second answer if you know the first answer. It involves adding or subtracting it from pi, or sometimes 2 pi. It depends. Okay, but we'll talk more about that. 2.498. Now, why did I put that plus 2 pi in? What does that represent here? Right. It's basically saying you could add 2 pi times 1, or 2 pi times 2, or 2 pi times 20. You can keep adding multiples of 2 pi, and you'll just keep getting answers in other cycles. So remember, n is an integer, positive or negative. Now, if they asked you to do this problem in degrees, you wouldn't be adding 2 pi n. Someone tell me, what is 2 pi equivalent to in degrees? Yeah, 360. So you'd be doing a couple things different. First of all, you'd be putting your mode into degrees. You would be setting your window from 0 to 360. Okay. So you can adjust this to do it in degrees as well as radians. You just have to adjust your calculator, and you have to adjust what you write on paper. Questions on 3A? Let's finish up, I think this is the last one, with 3D. Cotangent x equals 2.5. So it's the same idea. You've got to put y1 and y2. But I don't have a COT button. So how do I type cotangent into y1? Zach? 1 over tangent. That's cotangent. And now in y2, I'm going to put 2.5. Now, I don't want to confuse myself, so what I'm going to do is only graph one cycle. The formula to find the cycle, tangent and cotangent, is different than sine and cosine. Sine and cosine, thought I wrote 2, yeah, right there, 2 pi over b. Tangent and cotangent, pi over b. So Jared, what's b in this case?
2.5.
That's my constant on the other side.
X.
And the coefficient of x.
1.
1. If you don't see it, it's a 1. So, the cycle length of this graph is pi over b, in this case, pi over 1. So set your window from 0 to pi. You can just type 3.14 if you want, or just pi, it'll change it for you automatically. If you remember a little bit about tangent, this graph goes up and down forever. So you don't really have to worry about seeing the highest and lowest. You never will. But I would go at least -5 to 5 so you can kind of see the curve of the graph. And I guess I didn't do -5 to 5.
You can hit enter stuff.
Thank you. What did I do? Negative. Oh, I changed the scale. I meant to put -5 as the y-min. Although it didn't matter in this case because you can see, you can still see the graph and you can see the one intersection point. This graph has one answer per cycle. One answer in this cycle, one answer in the next cycle, one answer in every cycle. So just find this one answer. Second calc intersect. Should just be able to hit enter. And it gave me an answer of 0.381. That's just approximate. Plus, what am I going to put on the end to show that that answer repeats forever in every direction? Plus, yep. Plus the period times m. In this case, the period is pi. So the next answer would be adding 3.14 to that. The next answer after that would be adding 2 copies of 3.14. And after that, 3 copies of 3.14. If you want to go prior to that answer, just subtract 3.14, and that'll bring you earlier. Any questions on that? All right, so tomorrow we're going to pick up with more of these kinds of graphs. What we're going to look at tomorrow, though, is instead of just having one trig function on the left, we might have 2, like sine plus tangent equals 2.5. So now it's an equation that has 2 trig functions in it at the same time. We've never seen how those look. We don't sketch those by hand because they look very different. Okay? But that's what we'll take a look at tomorrow. All right, so we didn't really do a whole lot of different stuff, so there's not that many homework questions. So it's page 394, 37, 38, 41, 42.
And then 45 to 47, and 49 to 53. Reminder, I will be here after school on Thursday, should be. So if you need any extra help for the first test of the term, you can come then.